Hello everyone. Today we will be presenting about the ECE building construction plan. We are group 5. The team consists of Fadi, our senior project manager, Kinda Al-Kalal, our senior architect, Mohammed Hanzla, our consultant designer, and Omar Al-Masri, our interior designer. First, we'll start by introducing our company. Our company is ProBlue Contractors, founded in 1984. Our vision is that design is powerful and profoundly influences our daily lives and our sense of confidence, comfort, and control. We are committed to advancing the role of design in expanding opportunity and enhancing the experience for people of all ages, abilities, and cultures. Our mission is to have a human-centered design which describes our guiding principles. We support the global universal design, design for all, and inclusive design movements. We also think it is critical to be open to alternative viewpoints that may make sense. We will first start with the introduction. The ECE building, or the Electrical and Computer Engineering Building, first started construction in 2011. It was officially concluded in October 10th, 2014, and had an estimated total of $95 million, with around half of that financed by the state of Illinois. It consists of 5 floors, 1 basement, and around 230,000 square feet of usable area. This includes 20 labs, a grand lobby, conference rooms, and multiple open workspaces. It is built using mainly granite, bricks, glass, and steel. This material is recycled and all regionally sourced. The first section of this plan is the mobilization part. Okay, for the site context, the ECE building is located at the western corner of the North Quad. It overlooks Wright Street and its address is 306 North Wright Street in Urbana. It's surrounded by Beckman Institute to the north, the Coordinated Science Lab to the east, and the Micro and Nanotechnology Lab to the south. It's serviced by 2 main roads, the Wright Street and to the west, and the Eastern University Avenue to the north. On to the site limits. As seen in the Google Earth screenshot, we can annotate the site limits on this picture. First, you can see the yellow line. It shows the total site area. This was determined using Google Earth time-lapse and delimiting the fence markings that were able to be seen. Next, you have the dark red polygon. It represents the main building area of the ECE building. Then you have the pale red polygon. It represents the secondary building area. Then you have the 2 small red polygons on the left of the image. That's on Wright Street. These are the main entry and exit gates used by the trucks. More details regarding the path is explained later. The small black polygon shows the material below the material gates is the pedestrian worker entry to the site. Then you can see the blue polygon is the likely position of the temporary office spaces. And then the 2 yellow polygons are the staging areas. The larger one on the quad is material staging, while the one closer to Beckman is the equipment staging area. Note that the second equipment staging area is a potential location just from images of the construction site and the coming sites. Here you can see the basis of the previous claims. You can see that the image on the right shows the temporary office, the white structure, with the Beckman in the opposite direction, meaning those offices are to the south of the electrical building. And then the other 2 images showcase the material staging area being alongside the quad and the east of the building, as well as the equipment staging near Beckman Institute. In this image, you can see an excavator in the back in front of the building being built. This suggests that the area could have been used as an extension to the equipment stages, especially as we can see material being hauled around near Beckman too. The type of fence chosen is a chain link fence. Chain link fences provide transparency and also helps develop interest into the project by people passing by. The chain link fence is easy to place around the site and has sliding gates for vehicular access. It also has swing gates for pedestrian access. This image, as you can see, also shows the northernmost vehicular gate that was showed in the previous image. Here you can see the signing on the fence below. This signing acts as a source of information on the building's function. It showcases the future appearance of the building, and it also serves as a warning instructions, which will also be shown on the next slide. As mentioned before, fences hold warning signs. So the left fence has a red sign that says restricted area, keep put, and the right sign as seen has sidewalk closed. For the hauling routes, our materials are sourced from Prairie Materials at 3200 West Springfield Avenue in Champaign. We used Google Maps and Google Earth to check for the appropriate routes for the trucks. We use the route shown in the image in the sides, even though it is 10 minutes, which is longer than the fastest route, 9 minutes. However, this route was chosen because it goes through main roads that allows trucks to go under any underpass without any height limit. Okay, based on the following image, first of all, a truck coming into the north gate and going into the pale red area, which has a lower altitude than the rest and is overall empty, may be able to deposit some material or equipment at the location and turn around and exit from the same gate onto Wright Street and back on Route 2 mentioned above, which are the orange arrows. The second thing is a truck entering into the south gate would deposit the material and or equipment at their designated areas and loop around the building before leaving from the north gate onto Wright Street and then follow along Route 2, which is the blue arrows. So after the mobilization plan, we have the site and excavation plan as follows. As you can see in the image in front of you, these are all the identified utilities on site, and there's a legend where the red is the underground electric lines, the yellow are the gas lines, the orange are telephone lines, and the blue are potable water, purple sanitary and irrigation line, and green is a storm sewer line. Then you can also see where there's a utility replacement for the Beckman connection, since it's a new building. And you have to note that before starting any excavation work, site utilities should be rerouted, protected to a place that will not be affected by construction activities. After we have identified all the present and needed underground and overhead utilities on the site, then we have to determine which ones are going to be disturbed and need to be rerouted. First, you have the sanitary sewer line, the water line, the gas line, the telephone line, the storm sewer line, the overhead electrical line, the underground electrical line, the communication line, and the SBC communication line. These utilities are owned by different companies, and all the contact information and addresses of each utility owner is provided in the table shown in the slide. Onto the equipment required for site cleaning. First, we have the crawler-based dozer, which is used for removing trees of large size and concrete waste from the sidewalks. Then we have the excavator, which will be used for clearing stumps. And then we have the disc-style wood chipper, which will help cut down trees. For the demolition plan, as you can see in the plan in front of you, you can see all the types of demolition that will occur and where it will occur according to the legend and the highlighted place. Based on the demolition plan in the slide before, some of the items that are going to be removed are as follows: trees and hedges, parking meter and foundation, which is coordinated by the city of Champaign, sanitary manholes, electric lines, concrete curbs and gutters, and light poles and foundation. However, some items are going to remain and be protected. Some of them are trees beyond the structure, the water main, and specific structures and associated piping. Next, for the excavation, we have to calculate the volume of excavation. This was calculated based on the average length, average width, and depth of excavation, while also assuming the sloping of the sides, which is 1:1, and providing 3 feet for working space. The soil type was assumed to be loam, with 25% swelling factor. So, as follows, the total volume, or the estimated excavated material to be removed, was about 63,856 loose cubic yards. So then, for selecting the equipment required for excavation, we start by determining the production of the excavator based on the heaped bucket volume, job, and management conditions, bucket fill factor, and number of cycles per hour. Then we determine the number of excavators needed based on the volume of excavation on site. Then, to determine the number of trucks and loaders needed, we computed the total cycle time of the truck. Then we determined the number of trucks required by dividing the total cycle time by the load time of the loader, which then ended up having 8 trucks and a loader so that the truck productivity is governing. So the total equipment required are 8 trucks, 1 backhoe loader, and 3 excavators. The truck volume was 16 loose cubic yards, the excavator volume was 2.5 cubic yard buckets, and the loader had 2.5 cubic yard buckets. Then onto the excavation phasing plan. This can be completed in 4 phases. First phase is site work, then the part A of the building, then part B of the building, then demobilization. Phase 1, which is the site work, first of all, you contact the call center known as Julie to request a remote ticket entry at least 48 hours before needing to dig. Then you coordinate with Julie for a temporary shutdown. They will also handle the schedules with the utility locator service, which takes 2 working days. All the public utilities will be marked by a utility locator. Then you reroute and relocate all necessary services. Then on to phase 2 of the excavation phasing plan. You have the building section A, which is the north part of the building. The excavation work will start by surveying the area, setting corner benchmarks, coordinating the trucks, creating a ramp for trucks to move in and out of the site, which specifications of the ramp are on the slide. And then you have a storing earthwork area for backfilling. Then on to phase 3, which is section B of the building, which is the south part. As soon as section A has finished, the excavating will begin for building section B, and it will follow the same steps that were outlined in the slide before. Now, lastly, for the demobilization, before excavation has finished by a couple of weeks, you have to coordinate with the lowboy or necessary trucks needed to haul the equipment off the site. Before you begin to remove the equipment, you have to make sure none of the equipment being used are going to be used for the next phase, so you do not relocate or remove it off the project when you still need it. For the project, you have to keep at least 1 excavator, backhoe, skid loader on site to help place the filling material and help move material on the site. After the site work and excavation, we then go on to the foundation part. Now for the foundations. The first step to any construction is the foundation. First, we have to analyze what the foundation needs. First, we map the groundwater underneath the surface, which will tell us where the best places are to begin drilling a sump pump to prevent water from collecting in the basement. We then select the design working life, which is usually around 100 years, which is category 4 according to the Eurocode, as structural examples, including monumental buildings and civil engineering structures. Since it's not a very tall building or a skyscraper, there are only vertical loads and very few shear loads. Also, a soil survey will be done to find out the soil bearing strength. And then you have to see the frost depth, which is also calculated by consulting historical data to determine the minimum depth for the foundation. Next, for the footing selection, according to the soil condition and the load calculated for the superstructure, the suitable foundation system required for a project is shallow foundations or shallow footings, since the soil is relatively firm under the structure. This 4-story structure must have at least 100 kilonewtons per meter squared bearing capacity to consider the shallow foundation. This project in particular will have a combination of isolated and combined footings. For the equipment required for the foundation stage, first you'll need a vibratory compactor, which are used to compact the soil to its proper density. Then for pouring the slab-on grade foundation, a concrete conveyor is used. Then you also need a vibratory rammer, which are used to reduce air spaces in concrete, which is then followed by the screeding. You also need a power trowel, which are used to float the screeded surface and then provide a finish to the slab. Lastly, you also need a total station to measure angles and distances from footing to retaining walls. Additional equipment required are concrete pumps, which are used for pouring concrete. This specific pump in the picture is chosen because of future calculations. You'll also need a dump truck for transporting, a backhoe loader for digging, loading, and transporting and excavating. And you also need a crawler excavator, which is used for trenching, loading, and lifting. We will also need a telescopic boom lift, which is used to reach high vertical places to access the retaining wall to place the reinforcement and the formwork. You also need the vibratory rammer, which is shown in the image and talked about in the slide before. And you also need a telehandler for material handling and movement. Now for the phasing plan of the foundation installation. First, the property is graded and the foundation is dug. Once the footings are set and pass inspection, a contractor will pour the concrete into the home's overall foundation. Then the polystyrene blocks are installed for pouring insulated stem walls. The ground inside forms are prepped for the slabs. Then the plumbing pipes are run under the ground and stubbed up in the exact locations. Plastic tubing is laid for the radiant heat. And the concrete is pumped into place, and the site is cleaned up and prepared for the framing crew. For the building foundation phasing plan, the foundation will start from west to east within each phase. So they are split into two phases as shown in the figure. And then for the first part of the foundation will start with the footing on the north side. After the footings, the retaining wall on the north side, and in parallel, the south side will also start with the footing and then onto the retaining wall. After completing the retaining wall on the north side, the slab on grade is placed and cured without disturbing work on the other side. Now for the concreting plan. The total concrete requirement is 4,500 cubic yards. We are using 10 cubic yard concrete mixer trucks, so we need 450 trucks for the foundation part. This will be done in an interval of 15 minutes to avoid congestion. They'll also have nighttime transportation of these trucks. The material will be stored in the south phase of the project to work in the north, and then vice versa when working in the south. The material will be unloaded with the help of a telehandler. Then for the reinforcement material, the steel is unloaded in the staging area, then placed. And then since everything is cast on site, there will not be any prefabricated concrete items. Lastly, for placing the formwork, a telescopic boom lift will help access the heights for placing this formwork. For the footings construction process, first you have to locate the footing using a total station. Then the materials are transported using a mobile crane. Then you have the steel cutting equipment which cuts up the reinforcement and is placed. Then the formwork is placed. Then the plates are cut using the steel cutting equipment at site, and then they're arranged. Then the concrete is poured using concrete pumps, and the vibrators are used to compact the concrete. Then as soon as the concrete hardens, prefabricated rebar is then placed in the position. Then the formwork is removed and the concrete is cured. Then the backfilling is done with the backhoe, and then a compactor is used to compact the soil. And then onto the retaining wall. The retaining wall is built with the same process. However, the ground is compacted using water, and then the compactor will ensure that there is like a firm base for the concrete. This also helps to reduce the water absorption by the soil. Then the reinforcement is done according to the drawings or the design drawings. Then after that, the curing is also done using a water pond. Lastly, for the demobilization of the equipment, you have to return or relocate the equipment and materials. You create a list of materials that the company keeps as a part of the property and what is being sold or reused. The debris and the waste materials are then disposed of from the site. Then you remove the machinery once the work is done to create a pathway for anything to pass. And then halfway through the construction of the right part of the retaining wall, the machinery and materials are moved to the ground level storage to start the structure of the columns. Again, you have to make sure that none of the equipment or materials are going to be used later in the project before disposing of them. Now that the foundation part is done, we move on to the superstructure part. For the ECEB superstructure, it consists of 5 floors in a U shape. The building can be divided into 2 parts. Part A, the top 2 rectangular parts, as shown in the figure, and then part B is the middle square and the bottom rectangular part. The building is 209 feet in length and 240 feet in width. The main components of the ECEB superstructure are the I-shaped steel columns and the steel outer structure, the main steel girders, the secondary steel beams, the composite steel decks, which are 3-inch metal sheets and 4.5 inch of concrete, and the roof metal decking, which are 1.5-inch metal sheets. As mentioned before, the ECE building has a vast amount of concrete. As you can see here, the concrete calculations for each floor. You have the first floor having 622 cubic feet of concrete, floor 2 having 558, floor 3 having 666, and floor 4 and 5 having 311.8. For the ECE building, it has a typical framing plan with the main girders in the blue on the outer skirts of the building, which are connected by secondary beams that are shown here in green. This is similar for both Part A and Part B. Then for the steel connections, you have 3 types of connections. First connection is the secondary beam to main girders. These are shear connections and connected through the web, either welded or bolted, as you can see in the image. Then you have the main girders to columns. These are either shear connections or moment connections, and they depend on the designer's recommendation, as you can see from the 2 images next to it. And then lastly, you have the metal deck to main girders. The metal deck is welded directly to the girders, as you can see in the image next to it. For the steel proofing, all steel structures are sprayed with zinc coating for fireproofing, and some of the steel columns are encased with circular steel sheets to form piers. Then we have the equipment needed. We have the crawler crane, which is used for heavy steel erection, like the columns. Then you have the truck-mounted crane for miscellaneous superstructure lifting and easier and lighter structural lifting. Then you have the concrete pump for pouring concrete and composite decking. Then you have the concrete trucks for transporting concrete to the site. Then you have the telescopic lift, which is used for steel connection installation. For the crawler crane selection, we went with the Link-Belt 138 HiLab HSL. This was chosen first according to calculating the column weights. As you can see, the heaviest column, CG3, was 4.93 US tons. So we had to make sure that the crane can carry more than 493 US tons. And then you also had to make sure that the boom was longer than 127 feet, which is the height of the building. So accordingly, after checking the technical details of the crane, we saw that it had a 200 feet boom and can carry well over 5 US tons. Next, for the truck-mounted crane selection, we have the Link-Belt RTC 8050 Series 2. This was chosen according to the boom length and the max weight needed for assembling the crawler crane. So after checking the boom length and the radius of rotation, we saw that it was able to carry well over and assemble the crawler crane. So next to the concrete pump selection, we chose the Pump Partners Model 65M. This was chosen according to the height and reach. Since the maximum pouring height is 110 feet, so we chose this because it has a reach of about 180 feet, which is more than the width of the site. And then it can pump concrete to the farthest point on the highest floor if placed within the building boundaries. Then, while coordinating with the site layout, knowing the pump's dimensions, as seen as in the upper right of the picture, We selected 3 pump locations for each of the quadrants shown in the photo. So, for example, the top location would be able to access both the top 2 quadrants with ease, and then the right location would have the 2 adjacent quadrants, and the one on the left would have the whole strip. Then, for the final 2 equipments needed, you have the concrete truck, which is the Prairie Material Ready Mix truck, which we mentioned before was 10 cubic yards, and since it is easily locally sourced. And then we also chose the JLG 1350 SJP Ultra Series telescopic boom because of its length and achievable height. Next, as we mentioned before, we are going to split the superstructure phasing plan into Part A and Part B. As you can see, the Part A is the north part and the Part B is the south part. Before we go into depth about each phase and the rest of the phasing plan, we'll talk about the crawler crane placement. The crawler crane will be placed in the blue area, which can access both phase A and phase B and can work across the whole building. It can move from east to west, making it easier to navigate throughout the whole building. Then onto phase A, the process will go from west to east. It will go inward from the main street. It will go from part 1 to part 2 to part 3. First, it will start with a part 1 steel erection, which is the steel columns and so forward, and then the decking and then the composite slabs, going from part 1 to part 2 to part 3. Then, for phase B, the process will go the opposite of phase A. It will go inwards, outwards. However, then it will go from 4 to 5 to 6 to 7, which is from east to west, then back to 7. It will start with a steel erection in phase 4, then the decking and composite slabs, and then ending with the decking and composite slabs of phase 7. For the concrete pouring and pumping, a concrete pumper with a productivity rate of 220 cubic yards per hour will be used for the slabs. A typical floor, which includes all the phases from 1 to 7, will be poured in 3 days, with 318 cubic yards being the largest section. 8 concrete mixer trucks will be used to pour 105 cubic yards of concrete per day. These mixer trucks will be waiting on the street and will offload the concrete into the pumper. Dowels will be installed to ensure the continuity between the slabs, since the slabs will be taking place over several days. Next, for the steel storage, you can see that the steel storage, as indicated by the drawing, is in the bottom right of this drawing, which is in the north quad, within the site limitations. It's put there, or the storage was there, because of its easy access, where the crane can access the steel and then place or erect the columns easily throughout the building. Lastly, for the superstructure demobilization, first you have the crawler crane will evacuate the site using the ramp built on Wright Street. Then the concrete pumper will exit through the boundaries that were initially set, since it is outside the limits of the excavation. Then the boom lifts and the mounted cranes will remain on site because it's still needed for the installation of the envelope and exterior cladding. This also goes for any equipment needed for any later stage. Next, onto the exterior cladding and roofing. First, we're going to identify the exterior cladding types. ECEB has 5 types of cladding: terracotta, granite, aluminum metal panels, glass windows, and canopy HSS frame. The ECEB also boasts rain screen features like a double wall to keep rain away and provide thermal insulation. The glass also has the feature of enabling solar energy, thus reducing energy consumption. Then you can see to the right all the quantities in square foot of each cladding type. For the installation of exterior cladding, the installation procedure is as follows. First, you have the detailed surveying. Then you have to install the concrete masonry wall and insulation layers. Then you install the air barrier. Then you install the horizontal and vertical joist. Then you install the terracotta cladding on the joists. Then lastly, you install the insulation between the air barrier and the cladding. For the roofing structure, the construction is done in a sequence of 5 steps. First, it starts with the preparation of the roof. Then you go about installing the insulation foam. Then it goes to cutting the vents, cutting for the vents and pipes. Then you have the TPO setting and securing. Then lastly, you have the TPO heat welding. The equipment used for cladding and roofing is the crane assembly, as you can see in the picture. Then you have the telescopic boom lift, which is also used for helping the workers install the equipment, and the telehandler, which is used for carrying materials. For material storage, certain materials require different storages. For glass materials, they are more fragile than terracotta and granite. Thus, they require a more secure or careful storage. These more fragile materials require a safer storage location and are usually surrounded by safety nets, which help protect from potential falls or prevent breaking. Now for the phasing plan for the cladding. The deployment of cladding will be divided into 4 steps. It should be noted that all concrete masonry units will be complete alongside the superstructure to reduce the project duration. The first phase will start with the north elevation. You will first install mast climbers at the north elevation and install curtain walls. Then you will install the joints and begin the installation of cladding. Next, for phase 2, we're going to work on the south elevation. The mast climber will be shifted to work on the south elevation. We'll start with the installation of terracotta cladding on the back side, which is shown in the yellow color in the image. Then you install the glass windows, which is the green color in the image on the right. Then for phase 3, the west elevation, again, the mast climber will be shifted to the west elevation. Then you also start similar to phase 2 with the installation of the terracotta cladding, and then you install the glass windows after the terracotta to avoid any defects. And then lastly, you install, for this phase, you install the granite cladding after both the terracotta and the glass. For the final phase, which is the 4th phase, it will commence after all cladding installation is finished on all side elevations. The cladding at the center of the structure will finally be installed. This goes hand in hand with the superstructure process at the center, and it is also the final step of that process as well. Now on to the roofing phasing plan. For roofing installation, it is simpler than cladding installation. The installation will start on the west side of the building and goes toward the east side of the building. So it will go from west to east. This is because the west side has a lower elevation, means that the work will finish earlier. The image on the right shows the elevation difference and shows and signifies why the left side or the west side will be done before the east side. Then, lastly, for the cladding and the roofing, you have the demobilization plan. During the installation, regularly waste material is removed. It's moved from time to time, and while it's moved, the equipment is moved to the staging and storing area. Any equipment needed in the further phases is kept at the same location or kept on site. And then for the mast climber, it is demobilized by resting the platform on the ground, disconnecting the upper tires and supports, and loading it onto a truck. Now, after the superstructure, we'll be talking about the electrical part. First, for the electrical system components, the major components of a building's electrical system can be grouped into 3 categories: power handling equipment, wiring and raceways, and utilization equipment. Here we will discuss the power handling equipment. The first step in developing a building's electrical system is to examine how electricity is brought into a facility. The 2 main ways of feeding a building with electricity is from a utility line, either through running an overhead or an underground system. In this case, the ECE building, the system is used as an underground system through concrete ducts with separators or spaces. This can be seen in the slide in detail 3, duct bank detail. Then, there are 2 main feeding points, as indicated in the drawing, as input locations: the primary feeder and the emergency one. Also in this project, a new manhole is to be constructed as shown in the drawing, along with new ducts connecting the main feeding manhole and the power inlet, and also connecting the emergency power inlet and the generator. Now, after connecting the main feeders to the main electrical room, and the emergency room, which is shown in the figure, the main components of these rooms can be analyzed. The most important component to deal with is the unit substation, which is an assembly comprising of a primary voltage switch and fuse, or circuit breaker, a step-down transformer, metering equipment, controls buswork, and secondary low-voltage switchgear. The main function of this assembly is to accept an incoming high-voltage power supply, transform it to a lower one that can be utilized in the facility, and then distribute the low-voltage power through associated low-voltage switchgear. It is important to consider the placement and assembly of the unit station as soon as the substructural work of the basement is done, as it might require the use of a crane. Another important component of power handling systems are switchboards. Switchboard is a large, freestanding assembly of switches and fuses. The different types and comparison of the circuit breakers and switch fuse are going to be discussed in detail in the report. Then, moving on to the electrical distribution panel, it is essentially the same as a switchboard, but on a much smaller scale. Then, after the electrical distribution panel, you have a smaller panel board for floors, and they keep on getting segmented for each area. Lastly, for power handling, there are the emergency and standby systems. These use either two systems, an engine generator set or battery equipment. For the ECE building, the use system is the engine generator, which is a diesel set system, where a generator is connected to a main switchboard in the emergency electrical room, which runs on diesel. Then there's also an important note about the diesel generator. It has a concrete pad that has to be designed and poured on site prior to the room being built. Then onto the next group of components are wiring and raceways. The wiring and raceways are responsible for carrying the current throughout the whole system or throughout the whole building. These connect all the groups mentioned before electrically. For the wiring, the most common conductors used in wiring are aluminum and copper, and then they are usually insulated by various materials, depending on its use. These insulated wires can either run freely and can be boarded or nailed to whatever area they're in, or they can run in raceways, which are basically cable trays holding certain wires. For the last piece of the electrical system puzzle, you have the utilization equipment. The utilization equipment is essentially what uses the electricity fed to the building. So some of the examples of these systems are fire alarms or fire alarm systems, lighting, which are usually either normal lighting fixtures or emergency fixtures. You have pumping, you have HVAC systems like the air handling units, thermostats, and other machinery. You have audio and visual sensors like either TVs or projectors or whatever. You have telecommunication devices, and then you have outlets and device boxes. All of these are just utilization equipment which finish the electrical system components. Next, we have the electrical system phasing plan. This is split up into 5 phases. The first phase, which is the equipment installation. At this phase, after the foundation and basement walls are done, major components such as unit substations, emergency generators, large switchboards, and distribution panels are put into place with the help of a truck-mounted crane. This also includes the stage where the ducts and conduits are also constructed. The second phase, which is the distribution elements, is where the distribution of the electrical elements are placed. In this phase, all elements such as switchboards and panel boards, wiring trays, disconnect switches and junctions are installed. Third phase is the pull wires and terminate panels. This is where before the sheetrock is placed, and at the stage all wires are pulled to place and most panels are terminated. The fourth phase is the trim out, in which all accessories, fixtures, and utilization equipment are installed and connected to the building's electrical system. By the end of this stage, the entire electrical system of this building should be working efficiently. Last stage is the power and testing. Obviously, when you install any system, you have to test it to make sure that no fuse will break or bust, and nothing will go wrong. Now onto the electrical system equipment required. There are three main equipment required. First is the truck-mounted crane, which will already be there servicing the site. It's used to move and put all heavy electrical components into place. Then you have a concrete pump, which is used for pouring underground concrete ducts and for pads for heavy machinery. Then lastly, you have scissor lift, which helps access high places where you would place equipment or machinery. You may also need some minor or other special equipment. These are used throughout any other secondary construction, like electrical, mechanical, and plumbing and fire protection. These equipment are like common tools and equipment like drills, wrenches, and so on. You also need lugs, coax connectors, splicing connectors, and terminal blocks. You might need fishing rods or cable pullers, electric conduit benders, and then voltage testers and other machinery that are used for testing and circuit finding. Then lastly, after the electrical, you have the plumbing and fire protection. For the plumbing and fire protection system, the system components can be split into three types. You first have the piping, you have sanitary piping, drainage piping, which is for rainfall and other wastewaters, domestic water, which is split into hot and cold water piping, you have nitrogen piping, and compressed air piping. Then you have, for the equipment, you have a sump pump, a water pump, nitrogen storage tank, air compressor, vacuum pump, and neutralization tank. Then, for the fixtures, you have drains, either floor or roof drains. You have bathroom fixtures like urinals, lavatories, and sinks, and any other adjacent fixtures. And then lastly, you have valves, which are placed in pipes. Now, for the equipment used in the components of the plumbing and fire protection system, first you have the sump pump, which removes the wastewater from below ground level. Since drainage and sewage systems are usually based on gravity, anything below ground level needs a pump to pump it back up. Then you have the vacuum pump, which removes air from space, either for fire protection to change the pressure, so to avoid the fire going there, or to eliminate corrosive gases or any other materials. You then have an air compressor, which compresses air to increase the pressure. It's either for fire protection or for eliminating any other odors or corrosive gases. Then you have a neutralization tank, which changes the pH level of corrosive water. Since this is an electrical and computer engineering building, they might need neutralization tanks in certain labs. Then, lastly, you have a water pump, which pumps the water or the domestic water, either hot or cold, throughout the whole building. Then, for the equipment needed, which is fairly similar to the electrical equipment needed, you need the mobile crane to haul material. You'll need an electric scissor lift to access high places to install equipment. Then you either need a forklift or a pallet jack, depending on the size of the equipment needed and depending on the mobility of where you're going to install this equipment. And then you will need other miscellaneous equipment, which was mentioned in the electrical part, but one key miscellaneous equipment is a drill. Okay, for the plumbing phasing plan, the plumbing will be installed bottom up, like the building. The first phase will be installing the equipment and connecting it to the main water source or the public water source, which is offered by the city of Champaign or the university. This is both for the drainage and the domestic water system. And if there's any demolition or tie-ins to adjacent buildings, we will start off first with that. Then, for phase 2, the piping will be installed also bottom up, so you go from the basement to the first floor and then all the way to the roof, ending with the roof drain and the piping on the roof. Then, lastly, you'll have the plumbing fixtures installed. This ranges all the way from the lavatories and the urinals, to the sink, to the drains, to any fixtures that remain. All of this must be done before the gypsum board is placed. After placing all these systems, there will be a pressure test and a flow test for all the plumbing equipment to make sure that the building is running smoothly and the plumbing is running smoothly. Then onto the fire protection plan or phasing plan. The first phase will include the demolition and connection to the fire protection system tie in the Beckman Institute as seen in the figure below. This is done during the foundation stage. Then for the second phase starts after the plumbing, piping, and HVAC is installed. This includes the installation and connection of all the pipes and sprinklers for the wet system, and also connecting the piping and dissipation system for the dry system to the main HVAC system. Then lastly, for the fire protection plan, you have the testing phase. The testing phase is a very crucial phase for the fire protection phasing plan because it's always better to be safe than sorry. Then you have to test the system very well in case of a future fire. This is done before completing the drywall in the building. Now for the final stages of construction, framing and the interior finishing. Okay, for interior walls and partitions, the installation of interior walls and partition are done in a series of 3 steps. First, a runner is attached to the floor with fasteners. Then the top plate is connected using similar fasteners. Then studs are installed at the designed spacing. However, it is important to note that if the partition does not meet the ceiling, which means that it is a freestanding partition, end studs must be installed first. The ECE building has several types of wall framing systems. This include concrete masonry and acoustic assembly, two-sided assembly, acoustical gypsum assembly, and one-sided assembly. For the ceiling systems, the ECE building has 4 different ceiling systems. It has a 1x10 acoustical metal ceiling, a 2x2 lay-in acoustical tile ceiling, gypsum board ceilings, and wood panel ceiling system for the auditorium. All these systems can be shown in the key legend to the right and in the figure below. For the installation of ceiling systems, the installation of suspended ceilings are independent of the material type, and they are all done in a series of 5 steps. First, you install the hangers from above, then you ensure the levelness with a laser level, then you install the wall angles and connections to the main runners, then you install the T-channels, and then lastly you install the tiles or the drop ceiling material. After the ceilings, you have floors. We identified 6 types of flooring. You have carpet, wood, ceramic tiles, resilient flooring, epoxy resinous, and rubber flooring, which is only used for staircases. So then, for the floor installation sequence, it is almost identical to the ceiling installation sequence. It is done in 5 steps. First, you start by cleaning the existing floor. Then you prepare the surface using mortar adhesives and or padding. Then you place the flooring material and let it dry or cure. Then you fill any gaps using mortar. Then lastly, you clean up the finished flooring from any residual mortar or paint residue or any dirt that occurred while installing. Flooring is preferably done at the very end of the project in order to avoid any potential damage or staining from any construction process. Next, for the staircases, the ECE building has 4 main staircases, all being steel structures. Their erection occurs during the steel erection, however the finishing is done at a later phase, like the flooring phase. The finishing is done in 3 steps. First, rubber flooring is used and is set first. Then you install the guardrail glazing, and then you install the handrails. The construction sequence of all these interior framing and interior finishes are as follows. The interior wall framing is set before overhead MEP components are installed. This starts by attaching runners to the floors and top plates, then studs are installed to complete the framing. The framing remains open to install any in-wall component. After completion of MEP, insulation is set in the wall framing and then gypsum boards are set. Then any ceiling material is dropped in before painting. Flooring is done after all painting is concluded to avoid any tarnishing of the tiles. Ceramic tiles will be installed in bathrooms, while carpet, resilient flooring, and wood is installed per the design specs, according to what the room function is. The last step is the installation of any interior equipment and accessory like lavatories, water closets, and cabinets to avoid damaging them at any cost. Lastly, here are references we use throughout the project. This concludes our construction plan for the ECE building. Thank you for listening to our presentation. And if you have any questions, please feel free to reach out to us.